everybody. So now my time is here to start the session about reactive applications and about some reactive APIs. So I hope you know what you expect from this session. I hope my expectation is to teach you something new here. So I'll start with talking about reactive applications as a basis because very often people don't understand the concepts. But then I will talk about APIs that you can use to build reactive applications and how MicroProfile allows you to use this API more easily. If you have some questions, feel free to go to Slido, to the app, or to the web page. Raise questions there with the code GeeCON 2019. And before I start, let me talk a bit about the Java user group we have here in Prague. First, those who are from Prague or nearby. Yesterday, the GeeCON organizers were so nice to mention that we have an event after the first day of GeeCON, where Josh Long and Jürgen Heller came to talk to our Java user group. So if you haven't heard about the Java user group in Prague, feel free to go to java.cz to find out more and come to our next meetups. You'll enjoy a lot of good talks there, a lot of presenters, and the community. You can talk about things, and there's also always some networking time to talk to your friends or meet new friends over pizza or other refreshments. For those who study at the mathematics and physics faculty in university, in Charles University here in Prague, it's a good opportunity to come to our alma mater. Back again, for those who wonder where their colleagues studied, it's an opportunity to see a wonderful building from the inside, which is in the center of Prague. So now I'll follow with the agenda of my talk, or with the content of my talk. I'll talk about what reactive applications really are. Once again, I'll talk about it many times, but I see there's always it's always good to start with something in the beginning to explain the concepts. Then I'll show you what we have already in the API world, what we can already use to build reactive applications, and how these APIs compare. Some of the APIs are a good fit, like RxJava. Some of them are close, but not a good fit. But the good thing about them is that they are most of us know them, like Java streams, so we can get inspirations from there. Some of the APIs are standardized. There's reactive streams, which is an effort not only within Java, but to standardize reactive interfaces across different languages. There are very small interfaces, but it's important to be able to combine different solutions, providing reactive APIs. It got also to Java 9 as a Java util concurrent flow API. So this is now from Java 9 on, Java implements these APIs or has these APIs. It's still APIs. The libraries need to implement them, but if all of the libraries implement this same API, you can interconnect them, even if your favorite library uses some other reactive library underneath and you want to use a different API. And then finally, I'll explain where MicroProfile fits this world, how it tries to bring some standardization, some common APIs, and also improved APIs based on the APIs we already have, to simplify them, make them much more easily interoperable and easy to use. So first, let's start with the basics. Why we really want to do that, why we want to write reactive applications, what the reactive applications are. The concepts are not to be reactive or to be like a superhero developer, write efficient code. This is more, or at least I see it as more about the user experience. Reactive applications or the reactive manifesto, which describes how reactive applications should behave, was created with the intent of writing the best applications possible. And the best means they are performant, yes, they are efficient, but they are also responsive to user actions. They provide enough information to the user what's going on, and they are very user-centric. So instead of, if you have your application, instead of waiting for something to happen and freeze everything else, and the user can't do anything about your application or can see what's going on, instead you should be you should write your applications in a way where the user has the control. Or if it's not a user, it might be a client application that can react to something what's going on in your application before it just crashes upon it. So in order to improve the user experience, we need to have a different approach to some things that we were doing before or are doing now. So that's what reactive world is trying to accomplish or give us tools to do that. At the same time, we also want to save resources, because there's one way to make application performant and fast for user, but it's very costly. You can just throw more resources on it, but it doesn't really scale enough if you have expanding exponential number of users. Now you have like 1,000 users accessing your application concurrently, but in the next month or the next year, your company grows or your project gets more attention, and you didn't see that before. And if you design your application to be reactive from scratch, then the application is capable of handling that load much better with not much additional cost. Obviously, at some point you need to throw more resources on it, but the application is able to really utilize all the resources to 100%, not waste something while waiting, or lack of synchronization in the application. The worst thing is execute everything in one thread, because then when you give it a lot more CPUs, then everything is still synchronized on that one thread, and all the other power is lost. This is also a way how to keep with massive loads. So most of the time you don't need that, but there are companies, there are projects which really need to scale with massive loads, either all the time, like Netflix. Like not everybody is Netflix, but it's a good example. Or companies that have some peaks, like they sell a lot of stuff on Christmas time or before Christmas time, but not during all the year. So it's much easier to scale within these peak periods when your application is elastic and can keep up with these loads. And in the end, what is important in every application is handling failures. In traditional application, you have these safety try-catch blocks. You can catch an exception everywhere and then somehow handle it or ignore it. Oh, I didn't say that. You shouldn't ignore exceptions. If you do, just slap you in your face. Never ignore exceptions. But in a reactive way or a reactive application is much easier to, if you don't have the tools, it's very easy to like sleep through errors, because errors happen everywhere, especially if you distribute your application, if your application grows to run on multiple nodes, and network communication is involved. And these reactive APIs and reactive tools help us to manage the errors, and at the same time allow the programmer to build the application so that it responds immediately, not waiting, accumulating all the errors, and then giving HTTP 5.0 response to the user like after 5 minutes of doing something. So let's start with threads. There's a bigger concept of reactive on top of threads, but threads are a good example where we can start saving resources and make applications more efficient. Let's start with how most of the time we use threads in traditional business applications and banks and application servers. It's much easier to write like sequential code that runs on a thread, starts and stops, and then releases the thread to something else. while everything executed for one user, for one interaction, is synchronized on one thread. Then you have these thread pools to allow you to process parallelly more users, but that one request still consumes one thread. It's easy to write that code, it's easy to read it, but it's not efficient. It very often can happen that a lot of the threads are blocked. Some of the threads are free to be used, but what happens if your thread pool is exhausted and all of the threads are waiting for something, then you're stopped. In the better case, you just wait and you put the task on the queue. In the worst case, you have to start refusing the task because you can't handle anymore. So a reactive approach gives you some tools and also some ideas how to improve this. And the basic component in handling threads is to have a small thread pool, but avoid blocking the threads. So every time there is a block in operation, something that would pause execution without really using the resources you have, you delegate the work to something else, to the framework, to the tools, and you continue using your thread for further execution, or you release it back to the thread pool so that somebody else can use it while you are waiting for some action to finish. And when you need to continue, that something you delegated the work on will call you back and will tell you this is the data you were waiting for. It will start your callback, and it will find a thread from that core minimal thread pool that will use to run your instructions afterwards, sometime later. The core of this is asynchronous operations. You asynchronously call something and give it like your telephone number, call me back. You give it a handler, and the handler then is executed in some different thread. It may be the same thread, but if it's reused from the thread pool, but there's no guarantee unless you have some operational model in your framework or a library that guarantees that the same thread will be used. But then you have to wait for the thread to be freed. So there are also downsides. The general outcome of this approach is that overall your application is able to handle more threads, like increase the throughput, so more threads per minute, more requests per minute, but individual requests may take longer because you no longer wait the thread, but you still need to wait for the operation to finish, but then you still additionally have to wait for some time until one of these threads in the small thread pool is available to you. It shouldn't take long because nobody else is really trying to block these threads, so they're just trying to execute something on the CPU and then release the thread. But there's some small additional waiting time. So overall, like individual requests can be a bit slower than before. But if you have lots of requests, the throughput will be higher because there's less context switches in threads and less operations, and also like the resources needed for individual threads. If they sum up, they're much smaller. Each thread needs to reserve some memory for stack trace, and you can't just create infinite number of threads. So with this model, if you use this small core pool of threads, and you try, obviously it's best to never block a thread, but it's almost never possible to avoid it. So most of the time you don't block the threads. Then you can just call something when you need some data, release the thread, wait for it to happen, and when it happens, then you release the thread. The point is the threads are taken only when you do something, and for the rest of the time they are available for somebody else or later time for you. So now with this example, you can see these reds. I'm a bit of colorblind, but I hope they are red. These things, if we compare it to the previous one, there's these red ones are blocking on the right, but basically you take all the one thread all the time, which is the blue thing. Either you wait or you do something with the CPU. Here, you take the blue one. These are quite small. I hope you can see them. The blue one is at the top next to the IO call, but when you have IO call, you're waiting, but you don't see any blue thing on the thread, so it means that thread is not blocked. And in the end, when you sum up all these blue operations, this is where you take the thread to do the computation to really utilize the CPU. If you sum them up on the right side, you can see that multiple parallel executions still can take less than one thread all the time. Obviously, sometimes they crash, so they have to wait, and these blue blocks have to be delayed for some time. But this is how you can basically, in this model example, you can process three requests within one thread. If we reduce the pool size to just one thread, it would still handle all these 3 requests at the same time. You don't need any more threads. So that's how you make efficient working with the threads. That you only keep them for the time you need. Otherwise, you release when you need for some blocking operation to finish. As I explained, this leads to asynchronous nature. So you can't just call a method and wait until it returns, because that is the situation when the thread is blocked. So the API and the methods have to support this asynchronous way of calling you back with a callback, or more nicely with something like promises. In Java, it's very often completion stage. And at the later or more developed APIs, when you try to handle these situations reactively, you have observers. So you observe the multiple events, not only when the data is finally ready, but when just individual pieces of data are ready. So that you can process everything as fast as possible, respond to the user as fast as possible, give it a progress bar or any intermediate computation, anything, so that the user knows what's going on. As a code comparison, the code can get a bit more ugly than before, or just a little more complicated. In this case, it's pretty simple, so it's hard to argue if it's nice or ugly. You just call a blocking method to read data. Typically, it's a database or something from file. You get data. At that time, you're blocking. Until you get the data, you block. But it's very nice, very easy to write and read. You just need some data. There's an instruction to call to get the data. When the data is ready, I have it in the data variable. Then I can do something with it. But the thing is that the instructions below are only get executed after we get data. And between these 2 points, the thread is blocked. The thread does nothing but can't be used by somebody else because it waits in the method, inside the read data method. On the other side, on the right side, we have an asynchronous read data method. The difference is that the read data method only initiates the instruction. If it's database access, it only issues a select query or any SQL query, but it doesn't wait for it to complete. It will return to you, and you can continue execution of something else. It will give you a handler or an object which you can use to control what's going on with the method, with the background action, and you can chain callbacks to it. So we can then use methods like then apply from completion stage, if you get a completion stage from read data. And you can chain callbacks, build some execution pipeline that is called after you have data. But this is just declaring what's going to happen in the future. It's not going to be called after the read data method is returns, because it doesn't return data. It will just return as a handler. It will call. We will build the pipeline. This basically takes no time. And then you are able to do anything else with the thread. As there is a comment says, it runs immediately, almost immediately, after the build pipeline is built. The pipeline is built. So you can return from your method and release the thread, or you can do something else in parallel while you're waiting for the other asynchronous method to complete. That gives you power. On one side, it gives you power to release the thread and make efficient usage of it. On the other side, you can do something else while something is happening in the background. A typical situation is to controlling if the execution takes too long. So timeout typically in reactive world don't mean that you get an exception from the method because the method already returned. It gave you a handle. So you only can declare some callbacks. What happens if there is an exception? But in case of timeout, you can have timeout designed in the method, but if there is no notion of timeout, you can still control what's going on, even without if read data doesn't support giving you exceptions after timeout. You can still control the timeout. You can have a timer and raise an exception yourself in your pipeline and execute the pipeline as if the method threw the exception. So you have much more control over what's going on. You can even attempt to cancel the execution if the method supports it. So to go further, how do we code this kind of pipeline? How do we create these applications? Let me start with what we already have, what most of the Java programmers already know. There's a completion stage API in Java SE since I think Java 8. It's an API that allows you to simplify completion or asynchronous execution. There's one downside: it only works for the final result, so it's not able to process results like stream of results. Even if you have a list, it waits until you really get the list, and then you can act on the complete list. But that's one step. There are other libraries that implement full support for reactive streams, reactive operations, which is RxJava and Spring Reactor. These are the main libraries there that try to compete, although Spring Reactor is basically a next generation of RxJava. It's heavily inspired by RxJava, so the competition is not that big, but there are other APIs also outside of Java world, like Akka, which are equally good or even better, but they have different APIs. And what is in these APIs? These are reactive. What it means? There's a big difference between reactive and asynchronous. Asynchronous only means that you are able to execute something and continue using the thread, and then you get the results at some later point in time. But you can't control how fast you get the result. If there is a stream, if not often you have the option to really get access to the individual pieces of the result. And it's almost impossible to, or very hard to do, like infinite results in case of you want to bind to some service and continue listening on all the data it's generating. Reactive gives you possibility to listen on individual data streams or data pieces. It also has support for recovering from failures, which is not always the case for asynchronous. Asynchronous often provides an error handler, but again, it's only for the complete result. But reactive is able to process error or recover from errors for individual pieces of data, so you can decide if you just ignore the data or you fill it with some other default data or how to handle the situation, and then continue processing the rest of the response. And very important is control flow. Once you have stream of data with typical asynchronous approach, you can't instruct the data producer to pause or somehow slow down producing the data because you have much slower CPU or you have some other data that you're waiting for, and you can't process the data from the first consumer because the other producer is slow. So you need to synchronize and instruct the first producer to slow down or continue at a standard pace. And this is what reactive APIs also provide. provide you how to control the flow and basically stop or pause processing for a while. In order to add this into our application, typically reactive applications work with streams. Reactive applications evolve around events, which allow to scale. This is like the only technical, like I would say, technical part of the reactive manifesto, which says that events are one of the solutions how to make this happen. So events are asynchronous. That's a good thing. Events can be sent, like there can be multiple instances of events, so you can send streams as data events, and then you can react on them by subscribing to events, processing the data, and publishing more events. And another consumer can again listen to your publisher and attach to it and further modify the event flow and act upon the events. That's essential part of the reactive applications that react on what's going on as soon as possible. So either provide responsiveness to the user or to recover from failures as fast as possible to basically keep the system up and running as reliably as possible. So reactive pipeline processes data. You listen to the data, you listen to the errors, and also you have a completion handler in case the data stream ever completes. The data stream can be a never-ending stream, or it can complete, so you get notified when you can stop listening on it. There are existing APIs in the Java world that some of them can be used for this way. Some of them are closed. The most accessible is Java Streams. If you look at the Streams API, a lot of the methods look like they would be useful because they have all these mapping operations, filtering operations. So if you get streams of data, you could use these methods in theory. And basically also streams are streams. So why not use them to process data streams? The problem is there's no way to really subscribe to data publishers because Java streams are the publisher and the consumer is basically coupled together. You have a stream, you connect to it, you process the stream, and that's it. You can't reprocess the stream again. The stream is dead. You have to recreate the stream to be able to process it again. Another disadvantage is that it's inherently blocking API. Although the mapping methods are nice, but how to push the data further, that's the difference. And with Java Streams, the only way how we can process finally the data is to call a blocking method that basically iterates over the stream and aggregates the data either to collection or other data structures. So that's a no-go, although it can be reused. I will show you later. Then we have some specifications that's called reactive streams that goes to Java Flow API. This is part of what we need. So we go back. This basically covers the subscribe and publish parts at the start and the beginning. But there's nothing to standardize something in the middle. And then we have these libraries like RxJava, Project Creator that basically fill in the middle, and they're basically enough for what we need. So just to explain the stream API, you have a stream in the beginning, you have these nice filter, map, peak, forEach operations. These are nice except for forEach, because forEach will basically close your stream and will block for all the data to come and aggregate the data to something that you can put in variable. But otherwise, it looks nice. This is nice. This is a nice pipeline, although it's not reactive pipeline. So these are the things I already talked about. One notable thing is also the exceptions. When you use Java Streams and you have an exception handling one piece of the data, it will blow up. It will give you an exception, and you can only catch it outside. Either you catch it inside your own method, or you catch it outside of the stream, and the stream is cancelled. So you imagine you have an exception for the first element in the stream, and then you have to cancel processing, and you have to recreate the stream again, and then start processing again. With RxJava pipeline, the code looks like this. This is the same thing that we had with Java streams. The difference is that now we have error handling, which is built in. So we can, on top of our methods, we can specify a handler to handle errors that happen inside our methods. Also may happen in the publisher, so publisher can give you exceptions directly. You are able to subscribe to the data, but this means that this doesn't block you. It's just an instruction that this instructs the whole pipeline to start listening for the data, and for every piece of data that bubbles through all these goes through the filter, is changed by the map operation, then the send data method is executed, and the send data can somehow process it. The thing is that you also can add additional subscribers to this. So you can take this pipeline and combine multiple pipelines. It's not like Java streams that it just returns you an object and you have to pass the object to somewhere else. You can't really combine it, the streams pipeline. The downside is that if you look at RxJava Java docs, you have loads and loads of methods, loads of operators, because it's a fluent API to allow you to build nice pipelines, but it also means that the methods have to be defined on the same interface, and the more operators you add there, the harder it is to find the operator you really need. You have to go through all the operators or remember the ones you need and just use the subset you can handle in your head. And another thing is it's incompatible with other libraries. So if you use a different library in your project than one of your dependencies that you want to use, then you can bridge them, because most of the libraries nowadays support the reactive streams. But you have to create this bridge, and the result is that often you have to understand what these libraries do and how they work, and also the methods that they have. Sometimes there are conflicting methods, like one method has the same name in RxJava and in another library, but does something different. There are cases, there are examples of this. And another example is there is a method that does basically the same thing, but has a different name because the terminology in these libraries is different. So that's a place where MicroProfile has a value. MicroProfile is a collaborative effort. It's a project within Eclipse Foundation. It's open source. But how it differentiates to these libraries is that it tries to bring just the API, not the implementations. API that all these libraries can implement in the same way as they implement reactive streams. And with the promise that the developers can use the basic APIs from MicroProfile, defined by MicroProfile, and reuse it with any library that is implements it, and only use what's in those libraries, what is different, what is useful when they need it. But for most of the job, it's only necessary to use the core operators that are defined in these specifications. That's the aim. MicroProfile started as an initiative to standardize these APIs for working with microservices. So it covers a lot of use cases for microservices, like defining REST services, monitoring applications, defining health checks and metrics. What else is there? Also distributing tracing when you have multiple services and they somehow relate to each other. But after some time, there was also an initiative to bring in some standardization in the reactive world. And it ended up with two new APIs. One is for stream processing, which is basically the operators, the middle thing of the pipeline, which fills the space between the publisher and the like between subscribing and publishing, which is already standardized by reactive streams. So ideally, you have one standard which is reactive streams or Java 9 flow, and a MicroProfile API, and you don't need anything else. In reality, you might want to use some specific operators defined in different libraries, but you always can interconnect them using the reactive streams. So you can build part of pipeline with MicroProfile API, and then just small pipeline with RxJava, and connect it using reactive streams, publisher and subscriber. And then afterwards, after this initiative was started, some of the existing specifications like fault tolerance were amended to support reactive programming model, because they initially were created to support the traditional one thread per request model, but they added, they were given some more APIs or some overloaded methods and interceptors that also work when you return an asynchronous object from a method to allow you reuse the same power that's in the specifications for reactive pipelines. So this is how a MicroProfile API looks like. This is the same pipeline we had with RxJava. The difference is a lot of it is inspired by Java streams. And the idea was take what most people already know in Java world and combine it with how the libraries are written basically by our reactive experts. But these experts were trying to make something work and didn't think too much, or probably didn't think too much about terminology. So they picked one terminology they liked, another library creator, which is an expert in reactive programming, but he decided to use different terminology. And the idea was just to compare these libraries, take what's best from them, and also bring in the APIs most of the people know. And that's why the methods are named mostly or have the names borrowed by Java Streams API. Where a method doesn't exist there, then it's inspired by naming the terminology in the libraries. So that's why we have filter, map, peak. It's the same methods that we have in Java Streams. There's forEach, again, that's in Java Streams. And onError, onComplete are not in Java Streams, but they resemble very much matching methods in RxJava or other libraries. So this is how it compares when we have the stream pipeline, which is not really reactive, so it misses some pieces, but there is one-to-one mapping, and also the methods basically do what also Java Streams methods do. They accept the same lambda, so you can, if you have a stream-based pipeline, you can extend it to make a reactive pipeline just by adding some more methods to make the pipeline really reactive. And one of these methods is handling error. So it's onError. There's onComplete. As I said before, you handle data, you handle errors, and optionally you handle completion of the stream. The only other addition there at the end is the method run, which again brings the concept from reactive libraries, where you first build a pipeline, and only at the end you basically attach the pipeline to the publisher, so that the publisher only gives you data after everything is built, and then you can decide to really attach it to the publisher or just keep it somewhere ready to be attached. So if you forget to run to call this run method, nothing really will be done. Because even though the publisher P will publish some data, the pipeline will not be attached to it. So that's the difference, why the run method is there. With streams, forEach is already blocking, so it's already doing the heavy stuff of processing the data, getting the data from the stream. And basically, that's the same thing as the combination of forEach and run. It will first run the pipeline through the stream, and call your methods to aggregate the data that is at the end. To compare it with RxJava, you can see that there's also a lot of common things. Filter and map are in all in streams, RxJava and MicroProfile API. But then you can see how RxJava methods map to the MicroProfile methods, which borrow, if possible, borrow the names from streams. Do on each maps to peak, which is completely different. But if you know streams, you know there is a peak operation. And do on each basically does the same thing. It's just a longer name and maybe easier to understand because it describes that do something on each. But it's new, it's not standard. So the hope with the MicroProfile is that people come to the reactive world from standard Java, not from RxJava, because if you already know what you're doing with RxJava, you probably don't want to create an abstraction. But if you are just learning RxJava reactive applications, or you are just adding some bits of reactive approach into your existing applications, then it makes sense to start with API, which you'll probably already use for just plain stream processing. Then there's a method onError, which is heavily inspired, as you can see, with do onError, although it's simplified, it's just shorter, which is a concept you see in most method handlers in JavaScript. You mostly have just onError, or you don't have do onError. It's obvious that you're doing something onError. OnComplete is the same thing. The last thing is forEach is borrowed from streams to match with the subscribe, but while in RxJava the subscribe does two things at once. It attaches to the publisher and also attaches the callback that should be executed after the pipe or the data goes through pipeline. In MicroProfile, it's separated, so you have separation of concerns. You have just one method that is executed for each piece of data that bubbles through, and then you attach the pipeline. I'll just briefly explain also what's around these and how to learn these APIs about operators. In MicroProfile, it's basically the same thing as with RxJava. Everything is on one interface, one big interface, to allow you to use it in fluent manner. But this interface extends with 6 different interfaces, because these operators have different semantics. They are used in different places of the pipeline. There are consuming operators, which define how many of the data segments or data items you want. There are filtering, which decide which goes through and which doesn't. Transforming, which will change the data. And there are other like error handling, connecting. So you would use them differently, and that's also reflected at least in the documentation where we have separate interfaces. And you can, if you want to filter data, you go to filtering operators, and then you can find all the filtering methods. They are also all on, I think, Publisher Builder. When you're building a publisher or when you're building subscriber, they basically have the same methods. So it's also nice that the methods are abstracted to these interfaces and then they are reused. So if you want to learn the operators, it's better to go to individual interfaces where they are grouped. If you go here, all of the methods are in one place, and also some more methods specific to publishing and subscribing. If you go to each individual method, this is inspired by RxJava. The Java doc contains these marble diagrams which graphically, visually explain what's happening to the data as they come to the operator and how the data comes out, which data comes out. So I'm not going to describe this, but just looking at it and briefly studying what these marble diagrams mean, it's much easier to understand than reading the description, because the description can be somehow vague or confusing, while the diagrams show as an example what's really going to happen. This is an example how MicroProfile implements the standard reactive streams APIs. So at this point, even if there are no operators that you would like to use, that you have special use case, where you would either have to build your own operator, or there is luckily something in RxJava or some other library, you can use it. You just have to build, instead of running the pipeline, you just build reactive streams publisher, and then you can subscribe to it with RxJava API. So you basically separate the pipeline into two pipelines. One is using standard MicroProfile APIs, but if you need to use window, which like looks at more than one piece of data at the same time, this is not covered by MicroProfile, but it's sometimes useful if you want to just show like the average value of last 10 values, or last 3 values in this case. You with the window operator in RxJava, you can do it, and you can then connect it to the rest of the pipeline using these reactive streams APIs. Oh, sorry. To extend this, there's one more thing to do. I still talked about pipelines within one single JVM. This is the code you write, you execute once, you have one service, it's executed when there's some data, then the pipeline is processed, another pipeline can be added, but it's still within the context of one JVM. If you want to, I was talking about scaling. So in order to scale, we want to build our applications so that they can accept or get more resources. It also means more parallel nodes, more computers that are distributed, and ideally it will just happen. The pipeline would just extend to these computers, whichever is available or whichever has the service that is needed to accomplish the pipeline. And this is possible if you have a means how to connect to the publisher and send the message to some other subscriber somewhere on the network. So basically, we need to bridge the gap between the publisher in one JVM and subscriber on the other one. And this is extended reactive pipeline that is basically reactive messaging, because you implement message brokers somewhere in between your services. So instead of just having subscribe, process, publish, you first receive a message, then subscribe to it, process, publish, and then send the message to the broker so that it can be processed by somebody else. With MicroProfile APIs, it's also possible to bridge this gap, because the recent MicroProfile specification, which is called reactive messaging, allows you to use this API to specify how to create these remote publishers and subscribers. The essence of this API is that you can basically use any broker. The specification doesn't prescribe how to work with brokers. It provides extension points. So you have factories for message consumer and message publisher, and ideally you have a library for Kafka or for AMQP that you just plug in and configure, or you can create a factory for yourself. It's just an interface. I think there are 2 or 3 methods, and it's very easy to write for any broker. The API looks like this. It tries to be very simple, but it goes from simple use cases which are very limiting to bigger use cases which provides you more power as much as you need. So the basic thing is you can have a method with anything, returning anything, and annotation outgoing, and the only thing you need to specify is the channel, the name of the channel you want to use. This is like a publish subscribe method pattern where the outgoing goes out, so it publishes to the source channel. So the string returned by this method, when it's called, it will be directed to this channel, and then something that has add incoming can listen to this. So when the channel receives the string, then something that is able to listen to the string, so the method that has a string argument, can listen to this and is called by the container, by the engine, and anything that is returned. Again, if you have also an outgoing annotation there, then you can route it to some other channel. So you can involve multiple channels and extend this pipeline again in the same way as we were able before with the reactive streams, where you could connect two different pipelines through the same API. Here you can connect to different pipelines potentially in different processes through the same channel and then another channel and route to another channel. So channels are like these connection points. It can grow more complicated if you want to have more control about the pipeline within the methods. So in case you want to receive a message and then run some reactive pipeline inside your method, inside your handler, you can create the publisher and return it. And this can be either a reactive streams publisher, which is the standard, so you can use RxJava and turn it into a reactive streams publisher, or you can use MicroProfile Publisher directly and return just the MicroProfile Publisher builder. One more concept in this reactive messaging is that most of the brokers have the concept of message acknowledgements. It means the message is delivered to you, but the broker still needs a confirmation that something like a transaction or a commit that you were able to process the message. Otherwise, it will try to send it to you again after some time. So there are two options to provide this acknowledgement. One is automatic, so the container that calls your method, after your method finishes, it will acknowledge that you were able to process. If you give an exception, if your method gives an exception, then it will not acknowledge, and the broker will resend the message again. Or you can manually decide. It's the same as with JETA. You can and EJBs. You can either have like method boundaries, where method is started, the transaction is started, and method returns the transaction is committed. When there is an exception, it's rolled back. Or you can have a transaction object and call begin, commit, rollback as you wish. So it's the same thing here. You can either opt which is a default, use the automatic acknowledgement or turn on manual, and then you have to use, I don't have an example of this. Instead of plain object argument for your method, you accept message with generics, and the generics is of type of the object you want to be able to listen to. And this message wrapper provides you ACK methods. So you can you can access your object from this wrapper by getValue, or you can acknowledge and potentially there can be more methods to control processing of the object. This is all just by how you define your method, and the container will process your method, will see the annotations at incoming, at outgoing, and also the return types, the types your method accepts, and will adapt to it. So it will create a message wrapper if you accept a message interface. It will give you the plain object if you just accept the plain object. I already talked about channels, so I'll skip to fault tolerance, which is one last slide. And the fault tolerance gives you a load out of the box just by using annotations. You put either retry, circuit breaker, and it's very useful when you have multiple services to recover from failures in communication between the services. With the additions in fault tolerance which support synchronous programming, I think I have an example here, yes. This is how it looks like if you want to use it in asynchronously to call a method that is reactively calls something else to retrieve data, creates a pipeline, and returns a completion stage, which is not the actual result, but something like a promise to accept, to be able to access the result later. And the interceptor, the retry and call fallback, will listen to the not to the exceptions for these methods, which would normally trigger them. Like if there is an exception, it would retry and rerun the method. But it will listen to what will come from this completion stage. If it completes okay, then it's okay. If it completes exceptionally, only then, after later time, it will restart the method execution. So currently there are multiple implementations of MicroProfile. Some of them already support also these reactive APIs, but it's also possible to plug some implementations of these reactive APIs into applications and basically extend these MicroProfile implementations. And you're free to use them, to try to look at the MicroProfile project, to look at the APIs, to evaluate what's going on, because it's an open project. And the most important thing is, if you're in the future, if you happen to be using MicroProfile, you have the ability to influence the APIs, no matter which implementation you use. There are many, but you can directly go to the MicroProfile project, ask questions, or even raise some enhancements there and directly influence what's going on. Thank you very much for your attention, and have a nice day. By the way, if you come afterwards, you can ask me any questions. I'm sorry I forgot to check the Slido for questions because I don't have time. But I also have some t-shirts especially for those who are interested to talk about MicroProfile or anything that I was talking. I'll be more than happy to give you t-shirts or stickers here or outside. Thank you.